Welcome back to the workshop. We want to continue taking a look at a knapsack problem, and we've introduced ourselves, of course, the problem, and we've taken a look at sets, and now we want to continue our discussion on sets. So let's do that. So we can compare two sets, like we can compare two numbers, right? I can say that the number 7 is less than or equal to the number 42, for example, right? That's true. I can compare sets. And what we can do is we can say that one is a subset of the other. So if B has all of the elements of A, then we say that A is a subset of B. And we can denote this by A, kind of a sideways U with a line underneath it. A is a subset of B. This notation can also be read that A is contained in B or that B contains A. When this phrase is usually associated to B contains A. It's kind of like we could rewrite this inequality as 42 is greater than or equal to 7. These two things say the same thing, and these two things say the same thing. All right. I believe the textbook also gives the notation as A is a subset of B, and both of these notations are appropriate. Essentially, it works a little bit like the equality sign here in our inequalities of numbers. The inequality says that with this line says that it could be equal to. So for example, 42 is also less than or equal to 42. However, 42 is not strictly less than 42. So the notations are important. This one says that A and B could be the exact same set. This one says that they are not. For the purposes of this course, I don't think that there's any significant reason to concern ourselves with which one we're using, with the exception of where we talk about actual set equality and a few details with that. But we'll talk about those again. So let's take a look at some examples of subsets. Well, we've already seen a few examples. So for the automotive manufacturers, we know that Chevy, Ford, and Dodge are automotive manufacturers. So they must be a subset of all automotive manufacturers. So I'm giving it in our set notation here. So the list of elements and the set builder notation X, such that X is auto manufacturer. Excellent. But I don't want to have to write all of these out every time, and that's why I gave them names. So I have that A is a subset of C. And those are the names that I gave them in our previous examples. All right, another one. Let's see here. We took a look at, let's see here. We gave a couple of different ones. We might notice that G is a subset of, right, so we have G, 6, 17, and 47 is a subset of, well, it's a subset of Z. Okay, cool, right? It contains integers, so it is a subset of Z. So G is a subset of Z. That's cool. We also have that S, right? All of the integers greater than -24 are also a subset of the integers. So we have that, where did it go here? S is a subset of Z. But you may also notice that we have that G, the numbers 6, 17, and 42 is a subset of all of the numbers greater than -24. So we have three different subsets here, or subset relationships. And what we can actually observe, since both of them are subsets of the integers and G in fact is a subset of S, we could say, we can make a string. We can make a string of subsets. So G is a subset of S. The numbers 6, 17, and 47 is a subset of all integers greater than -24, which is a subset of the integers. So we can connect these much like we could say that 7 is less than or equal to 9, which is less than or equal to 13. Okay. And then let's look at one more example. If we let K be the set of all items, we could possibly pack for backpacking. So let K be a set of all items for backpacking. This is referring to our backpacking in the Red River Gorge example, our knapsack problem. So if we let K be the set of all items for backpacking, we could say that choosing the phone to bring and the hatchet, we said that one wasn't a great deal in terms of usefulness to weight ratio, but we could pack it, and we could pack with that the raincoat, right? We would probably want to pack more things than this, but this is one collection of items that we could check. We could check and see what the total usefulness is and what the total weight is. But this is a subset of all of the items that we could pack. Of course, it's just a few of them. Okay. So let's see here. We could go back a little bit further again. And if we look at the set P right here, we notice that this has the elements 6, right? 6 belongs to P, 17 belongs to P, and 47 belongs to P. And it actually doesn't contain any other elements. But those are the exact same elements over here that are in G. So G and P, right? G contains all of the elements of P. So P is a subset of G. But P contains all of the elements of G. So G is also a subset of P. Right? They're the same. And we get set equality. So G is the set 6, 17, 47. And we said that P is actually the same set, just written differently. So when we have two sets that contain the same elements, we say that those two sets are equal. And we would simply say that G is equal to P in this case, right? So in general, A is equal to B when they contain the same elements. And for our example, G is equal to P. So it can be useful to note that two sets are equal if they're subsets of each other, right? We said that G contains all of the elements of P. So P is a subset of G. And P contains all of the elements of G. So G is a subset of P. And that gives us that G is equal to P. That can be useful when you're trying to show that two sets are equal. If you can list all of the elements, then of course just list them. But there are many sets which you cannot list. Maybe it's a very generalized problem and there isn't a specific list, but you still need to show that the two sets are equal. That could be a bit of a challenge unless you use this. Excellent. So we'd like to take a look at the knapsack problem one more time, but we'll go ahead and do that in one more video. So I'll see you guys again soon in the workshop.